on Tuesday. Okay, so let's look at some structures here. So we know that if we have a face-centered cube, we have so we have the atoms that are at corners. How many corners are there? There are 8 corners. And what fraction of the atom sits there? 1/8. Okay, so these are 1/8. We also have atoms that sit at the faces. And how many faces are there? 6. And what fraction of the atom sits there? 1. And we also, so that's what we did with the face center. Now with the body centered, we had one just sitting in the middle. So if it's sitting in the middle and it's not touching any edge corner or whatever, that's obviously just 1, right? So I'm not even going to write that down. The other thing we haven't addressed yet, but it's going to come up in these structures, is the edges. So I can stick an atom. There are all kinds of different sizes here because I'm not very good at drawing, but here's our atoms sitting at the edges. So what do you think? How many edges are there on a cube? 12? You all agree? Yeah. So we got the 4 on top, 4 on the bottom, and the 4 going up and down. So there are 12 edges. How many or what fraction of the atom sits at the edge? So let's think of it this way. If I take another one of these cubes and stack it on top, then this is no longer a corner, it's an edge, and I have twice as much. So what's twice as much as 1/8? 1/4. Okay, so I've sliced this in half this way, and I've sliced it in half that way, and that's how I get 1/4. Okay, so sometimes you will see questions where you need to figure out what is the ratio of the ions, the metal and the non-metal, based on the structure. So if I have a structure that is face-centered cubic, like this, for the anion, so we're going to call that X something minus. We don't know how much minus, but it's an anion. And we have the cation at the edges. So our cation is going to be at the edges. And we want to know what the ratio is. We'd have to count how many atoms there are in a unit cell. Now, do you remember how many is in face-centered cubic? All right, so it's a good chance to go over this again. So if the anion is forming this face-centered cube, it has 8 atoms at the corners times 1/8, and it has 6 faces with 1/2 at each face. So this is 1, and this is 3. So there are 4, right? So it's 4x. If I have the cation at the edges, we said there are 12 edges, and each edge contains 1/4 of an atom. How many are there? There's 3. Hang on there. And I forgot, there's also one in the middle. You can't see it, but it's in that little pocket in there. So there's one there. So that gives us 4x. So this has the ratio mx. And that is, in fact, what goes on with sodium chloride. So with sodium chloride, you can kind of see the chlorine is forming that face centering. And there's the sodium sitting at the edges. And then if I turn it around this way, you can see this little sodium atom sitting right in the middle of that cube. Okay. So the sodium chloride structure can be described this way. I like to call it a three-dimensional checkerboard because it's just sodium, chlorine, and then in this direction it's sodium, chlorine, and then going backwards it's sodium, chlorine. So it's like a checkerboard, no matter which way you look at it. Okay, so let's try the structure where we have kind of looks like body center. Here we have the edges are all one. Okay, so that's all one element. We will call that X, well, we'll call that Y. And then in the middle, we just got sitting in the center, one cesium. All right. So how many cesiums are in this structure? One. That's easy. Fluorine, we have 8 edges times 1 8 equals 1 fluorine. So the structure, or so the formula should be cesium fluoride. Now, if we look at where cesium and fluorine are on the periodic table, does this make sense for the charges that they form?
So will you explain why we do like how do we know how to get to the 8 times 1 8?
If I gave you, so your question on a quiz might look like this. This is the structure. Tell me what the formula is. So you would have a picture drawn. And so you would see, there is something at the corners. Now, if it is at one corner, it is at all the corners. That's what makes it a unit cell, is that it repeats in all directions.
Okay. Are we given the element?
If I tell you the elements, you would tell me the elements. If I don't tell you the elements, you would just use like A, B, and C.
Okay. And then from that, like I'm just a little confused on, is the 8, what does the 8 stand for?
8 stands for there are 8 corners.
And then it's just the half of that, or the fraction.
The fraction of that.
Okay.
So what I'm going to look at is where are the atoms? If it appears on the corners, it's going to be 8 times 1 8.
Is that always the case? Is if it's
For corners, yes.
and for faces as well?
There are times when it could appear on just like the sides or just the fronts or just the tops and bottoms, in which case you would say, okay, it's 1/2 times 2 because it's just on 2 of the 6 sides. But I would specify for you, this only appears on 2 faces.
And then to get the formula, we essentially just have to add those together.
Yeah, so you say, okay, I have a 4-to-4 ratio. Let's make it the smallest possible ratio.
And you have a ratio.
Because we added up 1 plus 3 atoms in this unit cell and 3 plus 1 atoms in this unit cell. Having 12 edges with 1/4 of an atom means there's 3 of these red things total that are counted for by the edges. And then there's 1 stuck in the middle. So all put together, we have 3 red atoms in there.
Is that always like, that someone we just need to know?
You need to know how to get there. Like if you happen to remember, if it appears on an edge, it's going to be 3. I'm okay with that. You need to tell me edges equal 3. Or you can say edges, there are 12 of them, 1/4 times 12 is 3.
And that's only face center, right? Like this only applies for face center.
If something appears on all the edges, on any cube or any box, there are 12 edges. And if an atom appears there, it's going to be 1/4. If something appears on a face, it will always be 1/2.
So this one is 12, well, that, there's no.
There are no edges on that.
Right?
Okay, we're going to get to an example of that.
You said you will tell us if there's one in the middle, or is that something?
I will tell you. Yes. Yeah, because there would be times when it wouldn't be in the middle. Okay, so we also mentioned that a lot of these are based on the packing pattern. So this would be like, you could either think of it as a simple cubic with the cesium kind of fitting in that right spot, or you could think of it as just a body centered with the cesium replacing the one in the middle. And this one is based on face-centered cubic with things fitting in the holes. So first let's look at and this is true for face-centered cubic or hexagonal cubic because they're just the layers that are aligned. We have the two kinds of holes. So if I have 3 atoms on the bottom and one sitting on top, that's a tetrahedron. And so the hole in the middle is a tetrahedral hole. Okay. If I have, that is a tetrahedral hole sitting right there. But I could also have the hole that is here. So let me put on these guys. So the hole directly underneath this is surrounded by 1, 2, 3, 4. The hole that we can actually see is surrounded by 3 reds and 3 yellows. So it's got 6 sides or 6 corners to it. So what that looks like is this. So it's got 6 corners, but it's got 8 faces. 1, 2, and then in back 3, 4. 1, 2, and in back 3, 4. So this shape, an octahedron, and a cube are similar because a cube has 6 faces and 8 corners. This has 6 corners and 8 faces. They actually have the same symmetry, in fact. So a cube has octahedral symmetry. That's just trivia, not going to ask you. Okay, so this exists inside of there. In a face-centered cube, there is one octahedral, OH means octahedral, one octahedral hole per atom. Okay, so we said that a face-centered cube, actually one unit cell, has 4 total atoms in it. That means that there are 4 total of these octahedral holes within this atom. Okay. There are, oops, I should say 1. There are 2 tetrahedral, PD is tetrahedral, 2 tetrahedral holes per atom. Now, which things are going in the holes? Which are smaller, cations or anions? We talked about this a little bit on Tuesday. Cations are smaller because as we take those electrons away, the others get kind of sucked in tighter. Okay, so when we think about the ratios, the holes have the ratio for the cations, and the structure itself, the atoms, are for the anions. Okay, you had a question.
For all of these crystal structures that we looked at so far, for crystals with just 2 elements.
So far, just 2 elements, but we're going to see one with more. Okay, so if I'm just looking at a binary element, if I'm just looking at 2 different elements, I can think about what are the charges and thus what do the ratios have to be. So if I have the metal is positive and the anion is negative by 1, then having the metal in an octahedral hole would give a 1-to-1 ratio, right? But if I have the metal is a 1 plus and the anion is a 2 plus, then having the metal in the tetrahedral hole would make sense. Okay, so a lot of structures are just kind of based on this idea. So a lot of them have that structure. It is the structure adopted by sodium chloride, which is also called rock salt. So this one is called the rock salt structure. Okay, so sometimes when you're talking about what is the structure of this, rather than explaining to you what the structure looks like, they'll just say it's the rock salt structure. So it's just that 3D checkerboard thing. This one also gave us the 1-to-1 ratio. Okay, this works better when our cation's a little bit bigger. I'll talk about what the size needs to be in just a minute. And so this is sometimes called the cesium fluoride structure. Now, if I have, let's do calcium fluoride. And rather than trying to fill up the whole space, I'm going to try and leave things so that you can kind of see what's going on. Let me use my circles. I'm going to use the yellow circles for the fluoride. So I'm going to have one at each corner. And one on the faces. And then this is where it gets a little bit more awkward to see. Just trying to show the ones behind. So I've got a corner down here. So now I have 1, 2, 3, 4, 5, 6, 7, 8. But I've only got 2 of the faces with a dot in them. So I'm going to add one on the bottom. Everybody see how that's at the bottom? Okay. One on the back wall. And one on the side wall. Okay, so I've got bottom, front, side, back, top. So I think I got 6 there. Okay. So where's my tetrahedral hole? Here, to here, to here. That's my tetrahedron. Okay, and I've got one on top, and then I can flip this upside down and put one down here, and I can put one over here, and I can put one over here, and up on top, sorry, 4 on top, 4 on bottom. So that's how I get my tetrahedral hole. Okay, so if I have Ca2 plus and F minus, what does the ratio have to be? What does the formula have to be? CaF2. And the F's are the yellows, and I have 4 of those. So how many red dots do I need in here? And so the reason that I have 4 for the fluoride, because they look like there's a lot more, is remember that I'm counting the 8 edges times 1/8. I'm not edges, corners. And the 6 faces times 1/2. So that gives me 4 fluorides. If I want to keep the ratio the same, how many calciums do I need? 2. Now the calciums are going to be in those tetrahedrons, which are entirely inside. Okay, they're going to get as far away from each other as they can. So I'm going to have one up here. So front, top, left. Okay. I want the other calcium, which is positive, to be as far away from it as possible. So instead of front, it's going to be back. Instead of left, it's going to be right. And instead of top, it's going to be bottom. Okay, so this side, bottom in back, so there's the back, here's the bottom that I just dropped. All right, so this tetrahedron is gonna have the calcium fluoride. Okay, so that's how it fills those holes. What portion of the holes are the calciums filling? Is it filling all of them, half of them, a quarter of them? How many holes did we say were in this? So there are 2 for every 1 yellow atom. How many yellow atoms are in there? 4.
Okay.
There are 4. So how many holes are there? 8. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8. 4 on the bottom, 4 on the top, 4 on the right, 4 on the left, 4 in the front, 4 in the back. That's how we count them. Okay, so it is filling 1/4 of the tetrahedral holes. So sometimes the way you'll describe a structure is you will say the anions take on the face-centered cubic with the cations filling a fraction, in this case, 1/4 of the tetrahedral holes. Yes.
I'm confused about how we got to the CaF2
From here?
Yeah.
How many negatives do you need to cancel the positives?
Oh, okay.
Yeah, that's just Gen Chem.
Okay.
Yeah, that wasn't a structural thing. That's just making the charges back.
Okay.
Yes.
There a 3D picture of this in my book?
There is a picture of it, but I mean, your book is 2-dimensional. It might help you a little bit. Because it's, my drawing is a little bit off.
No, I didn't mean to.
No. I mean, it's like, I'm not a computer, like computers can.
Conceptualize, yeah.
Yeah.
So
Can you give us a step-by-step way on how to solve this?
Okay, so let me draw a structure. And then I will give you the step-by-step way. I'm gonna leave this information here.
are the red the calcium?
Yes. All right. One of the most important structures, has lots of applications in different areas, is the perovskite structure. So in a perovskite structure, a cube. Okay. We have, let's see how to describe this. A is in the center. This is all information you would be given. B is on the corners. And X, which is your anion, is on the edges. So you might be given a picture that has circles, or you might be given pictures that have fragments. I'm going to do the circles. So these are B. A, I'm going to kind of do a dotted line. And then I'm going to use an open circle for X. So the way that a unit cell works is it has to be able to be stacked against itself in 3 dimensions, and recreate itself without flipping it over or whatever. So if I'm stacking this in this direction or on top or going to the side, I'm going to end up with this same thing at every corner. So corners, if it's at one corner, it's at all the corners. That's just a rule. Okay. This will always work out to be 8 corners times 1/8 equals 3 atoms. Now, as you count them, label what kind of atom it is. Because when we did, the body center, they were the same atom. This and what was in the center was the same, right? So gotta make sure you're paying attention to, whether or not they're the same. Check the faces. To see how many have an atom.
Why is it 3 atoms and not 1?
It's one.
Okay.
Sorry. The faces that ends up being three. We've done cubes and then it's been right in the center. But you can sometimes have a structure where if it's tetragonal, you might have two things in the face, okay? You want to see how many faces have atoms and how many are on each face, okay? Most of the time, if it's on one face, it's gonna be on all of the faces. But not always, so that's why you're gonna check. So the number of faces times 1/2. And if it appears twice on a face, then you count it, each of those as a face. And label it with what atom it is. Usually edges are like the corners. It's not 100%, but usually the edges are like the corners. If it's on one edge, it tends to be on all of them. Okay, so you're gonna check the edges, and it is 12 edges. Or if you happen to be less than 12, the number of edges. Okay, so the box is always gonna have 12 edges, but if for some reason it was like, you know, only the side edges, but not the top and bottom, then you would only count the side edges. Each of those is gonna be 1/4. And then any atom that is entirely inside, whether or not it's in the middle, any atom that is inside the unit cell counts as a whole atom.